historically, we might say humanity's goal has developed to be able to look into the world around us and see more, right? If you think of what history is the script that changes about what reality is. And as that script is changed through history, it's been changed by being informed by new notes, by things that someone noticed, one person or many people noticed that hadn't been noticed previously, that gave rise to new connections into the world, new things to pay attention to, actually, right? So I think a good starting place usually might always be metaphysically that as conscious beings that are trying to make sense of the world we find ourselves in, the major problem starts with the fact that the world is impinging us with more information than we can possibly process, right? The number of photons hitting my body, informing me about something about the exterior world, has to be processed. And I have to make up the visual, which I then say have the experience of seeing, right, from that information. Whether I make it right or make it wrong, whether I'm seeing right or seeing wrong, the way that I have to process it has to be done by me. Okay. The big problem is that I can't possibly process it all. So there has to be some selection process that decides what things I'm processing to begin with, right? There's a prioritizing process. There has to be a logic built in that gives you a way to process anything. Because there's way too much to pick from, so pick. Right? You need some starting process to know what to pay attention to in the world. And the fact is, the history of humanity, the waking up process that we've gone through, and maybe you can argue we've gone up and down through the waking up, but it's been a history that's changed how we look into the world, right? The little comparison I'm thinking of is something like electricity. We live now in a world where we see the effects of electricity. There's nobody that would be unfamiliar with at least me saying the words, the effects of electricity. All right? You might be confused about what electricity really is, like every honest person is, right? But you agree that we're using electricity. You're used to it. You're used to machines that are based on using electricity. That obviously wasn't always the case, right? I mean, and before it was the case, it wasn't that people were imagining being in a world that had electricity and just weren't doing it. They were imagining being in a different world, right? One that didn't have electricity as an option. Now, their world still had electricity as an option. The electrons still existed. They just hadn't become aware of it. And when they weren't aware of that construction, or that feature of the world, there's no way to logically take advantage of it, to look into it, to use it some way, right? To build on it. So becoming aware of the electron and the atomic structure of matter, right? And the built-in features that those atomic structures maintain is the whole quest of physics. It would become a formalized thing. We call it now physics. It reaches much deeper than that, right? And trying to make sense of the world around you. But nowadays, we have a large array of measurements. So the birth of science attached this super weapon to consciousness. Consciousness values getting clarity of the environment, because if it gets things right, it can predict things right. If it's seeing the world entirely wrong, missing all the relevant cues, the important things, it's paying attention to all the wrong things. Here comes the bully about to punch you in the face. You're paying attention to whether or not his shoelaces are tied, right? You really can miss the world. All right, why am I saying this? Well, in our quest to understand the world, to understand it and be able to use more of what's around us, right? We're using the properties of things on Earth, turn it into electricity and doing things with it. We could have done that before, had we known we could. Now the question is, are there other things we can do that with? And you can restate that question slightly differently. Say, are there still features of the world that are measurably real, that we know are there, that we don't understand? And overwhelmingly, yes, right? In fact, so far in our history, we've gotten now to a point where we're leveraging science, we're leveraging measurement, systematic measurements, systematic recording of information, systematic attempts to make sense of the sets of information, right? And that's led us to a large set of constants of nature. All right, the parameters that belong to atoms. That's what constants in nature are. All the features built into atoms. And why do atoms have those features? We haven't got there yet. That's forward in future. That's where we're trying to go. We're not done with the story, right? What we're doing is taking all of those parameters, the speed of light, Planck's constant, the gravitational constant, the electric constant, the magnetic constant. There's 288 constants if we go all the way with the quantum chemistry, okay? We're thinking of them as parameters that describe things that atoms can do, and we're trying to understand the stage that allows all of those actions and just those actions. We're trying to understand the stage made from those actions, okay? So we're trying to take the constants in nature, systematically compare them, look into that comparison for the symmetry groups, whatever we can read out of it, and from that draw a picture that gives us a stage of reality that breaks apart systematically. And if you looked everywhere and found all the unique ways, it could be doing one special way many times somewhere, but found all the unique ways, that would represent all the unique expressions of this stage, which should be exactly the constants of nature. They would be the constants that are expressible by a stage. All right, that's our process. We've made a lot of progress in this process. We've now got a clear pattern being revealed, and we're going second guessing, checking, trying to see if we can make the pattern even better, but it's really patterned up. I think that's the thing to really point out. This has been looked for a long time, right? Any pattern to explain any partial set, let alone the whole set, of the constants in nature has been deeply desired. In fact, years ago I published on the coyote relation, right? And it's a relationship, a numeric relationship found between the masses of three particles, okay? And is it a coincidence? Is it not? That's the whole debate, but it's a pattern. So that thing is really debated about because it's a found possible pattern. Does it mean anything is the question. But if you find patterns, that's where you lead, right? You try to look, I found a pattern. Does it mean anything? Does it lead me to more patterns? Do I discover more from looking at this pattern? So we've clearly found undeniable pattern. In fact, even if you don't know what the characters mean, you can still see the pattern, right? In the constants in nature themselves, and we're interpreting them geometrically. We're interpreting them algebraically. There's an algebraic geometric structure that this is revealing to us. Internally, it's the hyperbolic figure 8 knot wrapping back on itself. So it's a double cover of the Giesecke manifold, which is the minimal 3 manifold. Externally, that structure is the n hypersphere of maximal volume, falling in on itself backwards, right? So we're thinking the outside is completely hyperbolic, the inside is completely hyperbolic, they're inversions of each other, okay? And the structure on the outside has, well, all of the hyperbolic surfaces. From the constants of nature, we're seeing very strong evidence that what the stage those constants are playing out on is the construction of that stage, the one that's responsible for the properties that we're calling the constant of nature. It's simply the simplest possible stage that could be geometrically made, internally called the 3 manifold or the Giesecke manifold, okay? Double covered on itself, so you've made a boundary like a hurricane wall, but you've also made the other side to match, and now you've got a stability, okay? So the simplest possible 3 manifold double covered causes the simplest possible internal stability. But when you have the internal whirling around, you have the external environment that has to counter it, and you have a different, it's out in different scale, it's external. So it counters a different way, it looks like a different thing. The inversion isn't a mirror image, it's an external inversion. It goes all the way on the outside inversion. Okay, so it's like a circle inverted construction. And that's what we call the n hypersphere of maximal volume. So it looks like the entire stage, the whole universe that's composed of 5 different bases, 5 actions that live on different scales, like rotations of much, much different radii, okay? All fitting together, causing a closed manifold structure. Closed meaning, and simple meaning that there's no gaps between the boundaries, but there's boundaries created. All the boundaries come in pairs, so they're maintaining each other. The simplest possible stage would be the hyperbolic figure 8 knot. A hyperbolic stage wrapping around on itself, making an out-of-bounds domain from the external region. The external region then counters to take on the shape of the N hypersphere of maximal volume, and it looks like the dynamics of all the boundaries therein are responsible for, in fact, define the constants of nature. So we have 5 really important boundaries. The Planck time, which defines the unit seconds and the limit in that unit, the number here. We have Planck length, I just remembered that this doesn't come out. Whoops. It's dark enough, right?
Orange isn't the greatest.
Yeah. Let's change that. And this is in meters, I should say it right. This also defines what a meter is. Okay, we're using this as the limit of the base. And we have the Planck mass, or let's do the Planck charge next. Okay, yeah, so again, defining another unit that we call charge, and we're really here talking about just the coherent units, the system of units that define the coherent construction of the actions of physics. So just the seconds, the meters, the coulombs, the kilograms, and the Kelvin. Just think there's a unit that we're assigning to time, geometrically, algebraically. We're giving it the value of 1. Okay, there's 1 second. Doesn't matter if we call it second, we just have to give it a name. But it's a thing that's going to be completely different, dimension-wise different. It's so radically different that it's a different dimension than all the rest of them we're listing. Right? If you're measuring something's length in time, how long it takes between 2 events, it's a completely different kind of measurement than how long, the distance between 2 points or 2 events. Okay, so the base that we're inventing now, in fact, the base we're revealing with these constants. So it's not that we made up a definition of the seconds and meters and coulombs, and we might as well put the rest of them in, and Planck mass and the Planck temperature. And this is in Kelvin and kilograms. It's always worth trying to focus on this a little bit because it's difficult to sink in at this point in history. It seems counterintuitive to the physics you may have learned, right? Unless you've gone far enough, you have to really look into this conversation to notice this. A lot of people are still holding on to the idea that these units are all random, and they absolutely are not random. In fact, we're still trying to define them. If we can get better and better measurements of constants in nature, then we'll have more and more digits defining these bases. Okay, so why aren't they all the way defined? Because we're not making them up. We're getting them from the constants of nature. Of course, then we make a definition, but we all know that that definition only has so many digits to it and we've cut off. We're hoping for more accuracy over time. So the bases that we're revealing by the structure in matter, in atoms, tells us that there are these special bases, meaning it's when we pick these specific things as bases that have these numeric limits, there's numbers attached to all these also, then all the equations of physics connect under just these scaling parameters without needing new scaling parameters when you try to connect more complexly, right? So we have certain base actions in the world that we can frame with mathematical equations, and different ones we can frame with mathematical equations. And when you're using these as the bases and keeping everything coherently together, you can do both of those things at the same time. The interface works together, you could say. Okay, so these are going to be the boundaries we're going to look at pictorially at the end. And to prep what you're going to see, we're just going to be zooming in. Okay, we're going to be plotting the phase of, say, for the Planck time, we're taking the equation for the Planck time that we have, and then we're making the argument complex There's two ways to plot it. 1 over x plus iy or just x plus iy. We're going to do both and zoom in towards the point 0, 0. Just check out how gorgeously fractal, how beautiful it is. All 5 of these then, those will be pictorial representations of these 5 boundaries that we are saying play a dance, they intersect in some way for every single constant of nature. It comes down to these bases, these cutoffs, these boundaries doing something geometric. That's the role, or that's the major message we're getting so far. When we have a balance between these boundaries, in fact, the insight here is we're revealing that there are boundaries, first of all, right? The first big insight was that there are constants of nature. Okay, and we collect the constants of nature, we try to get better and better measures of the constants of nature, but as we do, we realize that in order to get, when we get better measurement of this one, we have to check how does it relate to the other interactions that it can relate with, right? And then we have to tighten the math between everything as we go and define bases that make it the simplest to do that, right? That's what we're revealing by looking into the world and discovering constants of nature. Now let's keep in mind that just getting to the point where you're looking for a constant of nature, where you're measuring the speed of light, takes a lot of advancement, right? You may spend your whole life where you've never spent any time trying to measure any constant of nature yourself, right? I'd say that's very common. So we're talking about a concept you hold about the world that's not that common to reach yet, and we're trying to go much, much further. The first concept is that there's a bunch of constants measured, and those measured constants reveal coherent bases, all of which have exact limits according to the constants of nature. They both have coherent bases and exact limits. Both of those are surprises. Before this, we used to think that the frame shouldn't matter at all, right? All the laws of physics are completely independent of what scale you're on or what non-inertial frame you're on, as long as it's not accelerating, right? And this says, ooh, that's totally not true. This literally says that's totally not true. There are limits in each of the boundaries. Okay, so we're taking a lot of steps. We have to notice the constants of nature. There's lots of them. We have to systematically compare the constants of nature. Get familiar with what it means to have a coherent system of units, right? So understand that the modern physicist meaning of the second, meter, coulomb, kilogram, and Kelvin literally are a coherent system of units revealed by the physics equations and the constants of nature, okay? The connections of the whole thing. I mean, I think it's a pretty fair assumption that these things should all compatibly exist, since they do. And that's the assumption that leads to the revealing of sharper and sharper definitions of what these bases are in physics and what the limits are. But today, the revealed limits of these only go to about 5 significant digits. I think this one goes to 9, all of these go to 5, and that one goes to 9. We don't know more, meaning when we use the constants of nature to find the cutoffs, right? We compare the constants of nature and divide them to try to get units to go away or cancel down to 1 or 2 units. We can find the limits that way. And when we do, when we're comparing, trying to find these cutoffs from the constants of nature, we get contradicting digits or contradicting numbers past 5 digits. There's different ways to try to get a cutoff for just time or cutoff for just length, combining different constants of nature, okay? And when you use different ones to do it, you get actually differing numbers after those digits. So we just have to put an error bar. We know it this much and then don't know what happens. So this is what's known now for the Planck constants, okay? Only from the constants of nature. And mind you, we know the constants of nature that we're inferring these from to more digits than we now know the Planck constants. So there is no modern story for these. This is the big surprise of our current reach in science, right? That these limits exist, that these bases exist, and that together they define a coherent logical system whose entire set of parameters are the constants of nature. So explaining all the things that atoms can do to each other.
But do we derive the constants of nature from the Planck constants or the other way around?
Who's the we?
Well, when we come up with the Planck charge, for example.
Oh, they come from the constants of nature.
So the constants of nature first, so we derive this from them.
Yep.
Not the other way.
Yep. But yeah, let's be really, really clear about that. We've measured the constants of nature, and we started out with not so good measurements, 1 or 2 digits, right? And then we got in 3 and 4, figured out really fancy experiments to perform in CERN sometimes, right? We're talking about literally using the numbers that we get from CERN, the best measurements, using the tools that humanity has spent the most so far to make on, right? So the numbers we've tried the hardest to get. And they give us all the way up to approaching 14 significant digits, right? Our best ones are almost 14 significant digits of information. But these are 5 or 9 because you can get to them in many different ways. How do you tell me which one's the real way? Don't know. But both of them infer a boundary. All the ways you can get to this or to this or this, they all infer that boundary is there for the first significant digits as the same thing. Okay, so big mystery. Why does it change after that? We don't know. Why are they there to begin with? We don't know. We didn't expect that, right? It's a big step to get to the point where you understand even what these bases are referring about the world. These aren't bases we've picked to give just names. It's difficult to give a full justice to the value of those bases. This is revealing that in the constructive balance of everything we've seen so far, everything made out of matter, there are 5 important actual bases. Nature itself picked out those bases as important. The big reveal in physics is that there are 5 important bases. Okay, that's a very modern understanding to get to. But when you see that we have 5 important bases of what? The logical construction of physics. They're the bases on which it works, with coefficients of 1 or coefficients made up of these, right? Which we're counting as ones of the limits.
That's so much easier to think about 5 things rather than however many other things are out there. So
it is so much. In fact, that's one of the most profound aspects of this. What we're really saying is that we've now got 5 constructive limits that have been suspected for a while by physicists to play some important role, by the way. It's not just this is coming from nowhere. 5 constructive limits and the basis on which they act. We've picked exact definitions for each. Do we know we're right? Of course not. How could you ever know if you're right? We're trying to map the real world. Even when you get all the observations that you know of accounted for finally, there could be observations you've missed still. So we never know we're right. What we're doing is we decided to look into these limits and say, let's define them completely. How? Well, let's take them, the ones we know so far, and ask Wolfram Alpha what geometric hyperbolic action, what possible hyperbolic boundary could get us close to that number. And when we did that, we get 5 definitions of 5 different hyperbolic boundaries. And then we just say, let's take those 5 boundaries serious. Let's say that they're all the literal 5 hyperbolic boundaries that are doing these complicated dances together, sometimes squared, sometimes cubed, right, in different combinations, but they're doing all this dance together. Let's take them serious. And now that we can say we know all the digits we want for the Planck temperature or the Planck mass, okay? If those equations are right. Let's take them serious to see where they go. All right, that's what we're doing. We have just those 5 boundaries, and from that, we're able to then decode the entire structure of the constants of nature, using the same exact 5 boundaries every time, defining everything else from there. And the decoding process has revealed constants that play important roles in the construction, right, that are like pi, I, the golden ratio, right, the most important popular and beautiful geometric constant list that there is that are discovered so far. They're right there playing central roles in the construction, which really makes you want to look. The Fibonacci factorial constant, I mean, the entire minimal structure of mathematics that you might just decompose something and put it together with. All numbers related to that story are popping up here. That's what we're finding. We're never trying to claim that we're right. What we're trying to focus on is the point that when we get right, when we better understand this internal construction, we can see the dance these boundaries are doing and how that dance is actually responsible for those fixed parameters, we can start taking advantage of the constructive fixed relationships of those parameters. We can start building machines that do the actions that can be done, like grow a tomato plant, my favorite example, because I really want the future to have access to real tomatoes. We can do all those actions, right? There's no one that should be doubting that a tomato plant can be grown. So what we're wanting to do is understand every single interaction, every boundary exchange, why it happens, and then do it on purpose. So we copy the real growth of a tomato, perhaps way faster than a real tomato. Maybe we can get rid of all the things inhibiting it, or maybe you have to do the same speed. Maybe it is already at max speed. Either way, you can copy any process that naturally occurs if you understand these boundaries well enough. That's such an important point because we're not there in history yet, but if we understood this construction, if we understood all the expressions we call the constants of nature that come from these constructive limits, then we should be able to turn nitrogen from the air into a machine and output anything that you've ever seen. Anything made of matter that can stably be made. Right? That's the level of understanding that this is pushing towards. When you get there, we can make a machine that every human can own. And now the conversation of resources, status-based resource, is irrelevant.
True post-scarcity.
True post-scarcity. This is such a valuable goal that it's far beyond anything I can imagine happening, or imagine focusing on right now that would better change the world. This skips past having to focus on all the bad things currently happening, trying to process it, wrestle with it, figuring out how you can make the world better, and puts it all aside and said, let's figure out how to understand the world better, way better. Let's be way more systematic about it. Let's be way more meticulous and get the concepts of what these bases mean. And why is it those bases that maintain the logic of physics? Right? That makes them somewhat special. Until you can see that they exist, you're missing something very important. But when you see them as operation bases, something now is real. A field that can do electric or magnetic things becomes something physically real instead of a ghost magical thing. That is so valuable. Electricity is a proof, right? That's a transition, I think, recent enough that we can remember. What would it be like to not know about electricity? It changes your life. Right now, we're still stuck in a lot of negative posturing in the world where we're not necessarily making everything better for each other, right? Here's a way any individual can participate in that. Try your best to get yourself away from the noise and the drama just trying to distract you and focus on understanding the world better, discovering the built-in logic, structure, boundaries, and then figuring out the next step. What do those do? Why? As you do, you'll start to see the world more richly. You'll literally be paying attention to elements that you weren't aware of before, right? Right now, nobody alive is conceiving of the electron in our analogy, but of the structure of quantum mechanics. The internal structure responsible for the logic of physics and the expressions fixed in the constants of nature. It's such a big deal to see how beautiful it's going to be to get to the point to just understand those. Because when you do, you can get past war, resource war, right? All the tactics we now have of trying to keep things from each other, even though we have enough for everybody. We can get past that by undercutting the need to get from anyone else. Literally, your ability to understand the world around you can make it so you never need to go to the grocery store again. You can transform air, nitrogen, into any food you want. That reshapes the world, that reshapes our activities, our focus, and most importantly, the way we treat each other, right? We become a resource via imagination. Let's look at, here we go. Here's column 1. Of our constants. Well, maybe I should start out here. Here's the entire constants poster, okay?
Oh, wait, how many are there?
in the
How many are in the cluster?
288.
Cool.
Yeah. There's 288 equations, 288 expressions in the constructive arrangement of the boundaries in the bases of the logic of physics. It's a long sentence, but this is a beautiful pattern. It's hard to see from a distance exactly, but as you zoom in, you start to notice, I mean, I'm sure you're already seeing, there's a lot of repeats of some things. Now, why do I say it like that so vaguely? I'm trying to really call attention to something here. It doesn't matter so much that you understand the pattern you're seeing. If you can see a pattern, then we're now at a stage where somebody has seen a pattern in the constants of nature, and that is new. That is really, really new. Do you understand the pattern? Does that matter? This is what we do in science. We find patterns, and then we look for the understanding behind them, right? So the first thing is just look, do you notice a pattern? This, before I put the equal sign, is a construction of the Planck length squared times the Planck mass divided by the Planck time and the electron mass, all multiplied by pi, and then multiplied by this other half of the universal binomial factorization equation. And this is the square root of zeta of 2. Zeta of 2 is also famously known as pi squared over 6, times by j theta squared and our hyperbolic inversion boundary. Okay, this is the scale at which things are most symmetric hyperbolically. In fact, that reminds me of a fantastic thing I left out. Literally, our symbol is this big box, right? And this is equal to the Planck length times the Planck mass over the Planck charge squared. Okay. But the box itself is representative of the scale in our hyperbolic construction that has the most symmetry. Why does it have more symmetry than everywhere else? Because really we're talking about a structure that's really asymmetric in scale. Okay, something like this. Well, way more than this. But to make it so you can still see it and I can draw it, let's pretend we're talking about a conic structure that's really, really not balanced. There's one axis that's completely more than the other. In fact, when we're starting out, one's infinity and the other one's not. Okay, so the ratio is right all the way. But here in a quantized one, where one's just much more than the other, if you draw a square, let's see. This is what you would see. Okay, we're going to keep the middle in the middle, but we're going to zoom in now with our square. What happens as you zoom in? Well, right now, this intersects here and here and here and here.
The points move out.
Yeah. If you shrink your box, or if you imagine blowing up the background behind it, either way, then you see the intersection points move outward, right? Necessarily. Okay, so no matter how different it is, except for maybe that infinity to non-infinity case, this ratio is going to say, or this structure is going to demand that at some scale, these things have gone out enough to be exactly at the corners. At some scale. You might have to zoom in really far to get there, but it doesn't matter. The point is, under that conic construction, if you've got cone on cone, no matter what scale the cones are actually scaled by, there will be, just fix one scale, put it there. Now zoom in until you find the case that you get this exactly, all the way through the middle there, and all the way through the middle there. And on this scale, you get this extra 45 symmetry thing. You get this extra square, or another fold of square symmetry happening. Okay, so what we're interested in is actually, let's draw a prettier picture. The scale in our hyperbolic construction that has that 45 balancedness in it on the cone. Okay, so let's draw it. we got the cone. Let's say, does that look about 45-ish? Okay, like that. So we're on that scale, and the scale, I'm imagining now we've cut off, we've zoomed into 10 to the negative 7. To make a hyperbolic construction at all, let's start from there a little bit. Let's back up a little bit and say, wait a second, if I just wanted to make a hyperbolic construction, what are my options? Let's start, imagine we've got an infinite void we're in, and we want to turn some part of that void of any size into a hyperbolic balanced arena of some sort. Some subpart of the infinite void. You want to make it be hyperbolically doing things. But you want to be able to come back later and say it's still hyperbolic. So you want a hyperbolically balanced arena, so it's persisting, right? How do you do that? What are your options? Well, like we were saying earlier in the video, the simplest double cover of a 3-manifold, the first simplest thing you could anchor yourself on would be the hyperbolic figure-8 knot, right? So this is really interesting. We got the hyperbolic figure-8 knot setting our scale, which is really now going to be analogous to setting our scale of seconds, okay, our base clock of everything that's going on. And then our external construction here has 2 division boundaries. One we call charge. This one is mass. And then we have 2 under the same exact balance. Let's see, maybe this one might be darker. Let's try it. With this same balance, if I'm calling both these black surfaces, these are 2-dimensional surfaces, this continues to go around, okay? This is a surface, 2-dimensional. But these are our division surfaces. These are our boundaries of division in this balance. And there's 2 of them acting against each other. But the reason it's a balance is because in the process of acting these 2 division boundaries against each other, we create this surface, the one-sheeted hyperboloid. It looks about like that, but it goes between this one and that one, right? It goes between them because it's literally made by the middle of those 2 division actions. And then we have this one sheet, or double-sheeted, so 2-sheeted, but it's imagined to be touching at infinity at the back in hyperbolic space, okay? Those are both boundaries put into balance under this hyperbolic construction. If you've achieved hyperbolic construction, you've got some scale that's doing this. It's got 2 two-dimensional surfaces and that are green, that are balanced surfaces. These are the boundaries of the smooth projected logic. These are the division boundaries where it is broken, the whole thing making the construction. But now we can kind of visualize what hyperbolic logic means. It means that there's somewhere that there's literal boundaries that are dividing these complicated ways. There's several things happening here, right, that are balancing against each other. 4 external expressions determined by the actual scaling parameter. Remember, we've zoomed in from the get-go to the right scale here. But it could have been, you could pick a different scale for hyperbolic geometry, right? You could imagine pulling these surfaces closer together, and then these things are further out. So it changes where that actual scale is in the scale of zooming in. Picking an exact scale is the other degree of freedom here, but the degree of freedom maybe it would have been too little to say before, to just draw the distance from here down to here. Call this the mass gap, or the gap that the seconds is inverting on. So the hyperbolic figure-8 knot externally is inverted as the n hypersphere of maximal volume. It is all of the volume between this surface and the cone, right? This surface and the cone, the volume of disruption of total is the inverse hyperbolic figure-8 knot. And it is literally responsible for why all those boundaries are there. So once it's set, the hyperbolic figure-8 knot is set, we have 4 external boundaries looking like this. The first one that set it is the one that picked the size of how far we're reaching out, how big we're making this distortion.
Now, you said 4 external boundaries. Do you mean 3 external boundaries, or?
These 4. Because this one right here is space. Space. And this one is temperature.
So where is time?
Time is the gap that created all four of those. Right here, we're only looking externally. So in this picture, you can't see a hyperbolic figure 8 knot because we're on the outside. But the hyperbolic figure 8 knot is exactly what's responsible for setting the size of the hyperbolic structure outside. So it reaches this way out and this way out, filling out, it's inversely filling out the construction of the N hypersphere.
So if time slows down, does the mass gap get smaller or larger?
Well, here's the cool insight. If the Giesking manifold is the minimal manifold, or the double cover is the minimal thing you can knot up on, okay, and have a coherently bound continual boundary, then it can't be less. This is the first size, the first gap, right? The Planck time sets the first size gap possible to make this hyperbolic balance. Okay, which makes it really profoundly beautiful to see what's going on, right? This is literally the structure inside, except for we've idealized all the boundaries and we didn't quantize them. We just need to chop them all up and have all the chop ups match a certain way. Details we're still filling in, but we're getting close to the whole structure. This is all the balanced boundaries, the green, all the division boundaries, the black, and those actions are literally existing with each other, right? They require each other. There's a maintained balance that's four-dimensionally maintained over one fixed gap. I'd think of it as just being fixed by one parameter, but it's really the whole inverse volume action that you've pushed things around by that is the gap that we're talking about. It's the distortion you've made in the fluid that now makes the whole fluid want to move. The total collective external gap. Yeah. It's really getting beautiful, right? Getting beautiful. Now remember, as far as a factorization theory, which is one way we try to look into, the darkest one, one way we try to look into making sense of the world in physics would be to have a true factorization theory, have a theory for how these boundaries could be breaking apart and reordering to do things that we need done, right? Well, when we note that we have these exact 5 boundaries and one equation that defines the factorization structure of the external arrangement of those boundaries, that's a pretty short description for the stage, right? Really short. Remember, our equation is this: 1 over x plus x cubed over 2 pi. And I need a darker one. Equals I to the I to the negative pi over 2 minus the scaling parameter externally is matched to the value of the Planck mass. So this is the constructive arrangement, a hyperbolic constructive arrangement. This equation is talking just about that, of these boundaries outside. So it allows us to find the roots of how they're fit together. Right? I mean, if you solve for this equation and find what x could be to make this equation true, then you get 4 solutions, it turns out. And we call them J1, and I'm going to say plus J2. I'm going to go ahead and add them all together, plus J3 and 4, and we find that the sum of these roots is equal to 0. That's interesting. It's interesting. We're getting somewhere. We have a constructive arrangement that's hyperbolic. It's Mobiusly. There's some inversion happened, twisting, closing itself to keep our anchor, right? But other than that, we're just hyperbolic. We've got our scaling parameter set to the mass boundary, the Planck mass boundary. Very interesting. And our roots sum to 0. But they also have a product. Of 2 pi and a quadrant negative 4 pi. All right. Another way to word what we're trying to do in understanding the constructive map of the parameters of physics, the external map of our world, is we're trying to describe how a 3D sphere, imagine we projected a sphere into the universe, right? It's a domain where balanced logic is happening, so atoms can exist, but it's a sphere, it doesn't go to infinity. But that sphere somehow on the inside can't be three-dimensional anymore. We have to go from a three-dimensional sphere, the one that's really easy for us to visualize, to imagine, but on the inside, somehow it transforms into a four-dimensional hypersphere. Okay, that's the task. Now, no one's ever achieved this task before, so don't feel too intimidated to try, feeling that you're not smart enough. No one's achieved it, so this is a really important goal to focus on. What does a three-dimensional sphere that transforms on the inside to a four-dimensional sphere look like? Okay, that's the Hopf map. That's what the Hopf map encodes, is that transformation. It's really complex, so if you're imagining something simple, you missed it. Here, we've got a rule for how things are hyperbolically, Mobiusly held together with this as their scaling parameter in that hyperbolic construction. And we've got a rule for how those roots sum what their product is and what their quadrance is. So this is telling us that we have a domain that's dividing up a projective sphere. That's a real good start, right? That the product creates a circle, maybe it's the inner throat circle, maybe, right? But their sum creates a balance. Great start. Perhaps one of the most exciting ways to look at this is to remember we've been looking very specifically to find a way to relate and explain the constants of nature. We want a partition theory of how things break up that way, right? And here we're getting a constructive theory that has 5 bases, 5 boundaries of 5 bases, okay? And that constructive theory puts those bases together under this prescription, which is hyperbolic and, in one way, Mobiusly bound, okay, to make our decomposition of a projective sphere. It's a great start. It's a great start. First of all, we have boundaries of bases, so we know what we're physically talking about. We literally have some hurricane wall of some size and shape happening somewhere, okay? And we're fitting them together. But when we do, we partition a construction that maintains a balance but also maintains projectively a sphere. It's quadrancing up a sphere, right? And it maintains a circle. It produces a circle. You should say the product is a circle. Okay, that's fantastically short and simple as a story for how you can get a hyperbolic universe into existence. To start from nothing and to make a hyperbolic universe. You would go to this one. This would be a good one, right? Because it's hyperbolic. It's based on, the Planck time one is based on the hyperbolic figure 8 naught, so it's the minimal possible hyperbolic. And then we have these other boundaries, these other scales of actions interplaying in that balance externally. And we even have the prescription for how they're being divided up, how the whole space is divided up, where the roots of the construction are, okay? These numbers define the roots. Now we can throw in one more detail. If we're drawing where those are, J1 is real close to the 0 on the x-axis, but it's not. It's got some positive value there. J2 is right here. 2 and J3 is roughly up here. J4 is its mirror down here. There are 2 other important variables in this construction that are just different parts of this, we should mention, Jr and Jθ. So if I were to start from the center and draw a line to J1, it would be a very short little segment, right? That would be the real value, the length of that segment would be the real value of J1. Happens to be exactly the same as J1 because there was no imaginary component to that one. But I could imagine doing the same thing for J2. Start from the origin, go all the way to J2, and that number would be the real part of J2. Again, the same as J2. But if I do that for J3, I'm going to be going in a real and an imaginary direction. And I'm going to have a length. So start from the origin, not from J1, and go all the way to J3. There's going to be a length to the arrow. It's not the same as to J2, by the way. It's a different length. It is the same as the length to the J4. So the length of this arrow, the longest thing from the origin in the system, is Jr. It's also here. Okay, so those are related directly to these, just different descriptors of the structure. And also, if you start from the origin and go to there and measure, this is J theta, or if you did it from here to here, it would be negative J theta. Okay, so you can talk about the system in polar coordinates or in x and y coordinates, right? That's what we're saying basically. So Jr and J theta are both part of this exact structure. Now, when we want to look, this is really a complete descriptor right here. This is our algebraic base for how the roots themselves are in harmony. If you want to ask, well, what are the partial expressions created by this decomposition structure, this hyperbolic decomposition structure? If you wanted to ask that, then you would have to ask, well, one, you need, in order to be an expression, it needs to be real. So what are all the possible real subsets that this construction holds? Okay, they need to be real. Let's try a couple just to make it clear. You could say, well, subsets, these are all made out of 4 things. So a subset, and it must be less than 4. It also needs to be plural. Okay, great. So we're just looking about pairs and triplets. How many pairs of this construction give us a real output? Let's try J1 plus J2. Let's just take the first 2. If you add those 2 together, you get a real number plus a real number gives you a real number. So that one works, that one counts. If we take, say, J1 plus J3, now we have a real number and a complex number, and the output is complex. So that one doesn't count. It doesn't have a real expression. That combination doesn't have a real expression. We're just going to look for all the real expressions, the pairs in this. So these 2 count. These 2 count together because 3 and 4 are both imaginary. They're both complex, I should say. They're both made out of imaginary real parts. But their imaginary parts are exactly opposite of each other. So when you add them together, those 2 parts go away, and the result is just real. It's negative, but it's real. Okay, so 3 and 4 count as another pair. 2 and 3 don't. 1 and 4 don't, right? You have to get either both of them being complex or both of them being real to add together to get a real output. Great. So then we get a set of pairs. What about 3? Well, if you're going to have 3 on this first row, you have to have, if you had these 2 together, then you have to add one of those 2 to it, and that wouldn't work because it would just be real and complex. Nope, won't work. So if you're going to have 3, 2 of them have to be 3 and 4. So you can have 1, 3 and 4, or 2, 3 and 4. Well, those are your options. Great. We've finished this row. Oh, you can also put minus signs instead of pluses. That's the other half, right? Now, this row, we need to get which partial sets of this constructive parameter in our decomposition structure count as pairs that give us real outputs. J1 times J2, a real number times by a real number gives a real number. Check, that one works. How about J2 times J3? Nope, same reason. J2 times J4? Nope. 3 times 4? Yes. Okay, so you get the picture of what we're doing, and you can also do minus sign, plus and minus all the way through, but we're just looking for the pairs and then the triplets. Which triplets again here work? Same set. So if you're going to do triplets, you need to have 3 and 4, and then one of those. So 1, 3 and 4, or 2, 3 and 4. Great. Real outputs in. So how do we say this again? We have this constructive arrangement in a hyperbolic Mobius decomposition structure, giving us our roots of that structure, our j's, but also the sum, product, and quadrants of those roots. So it gives us a look into what those roots are doing. What geometry are they acting on? They're the one that's maintaining these. Okay, beautiful. Now, when we want to look closer and say, all right, within this structure, within this projected sphere that's decomposing with some internal throat somewhere that's making a circle, but still projectively balanced, within it, what are all the expressions, all the partial expressions I should be able to measure? Great. How would you do that? Well, we take all the things that are real expressions, but partial. Need to be at least two, still plural, okay, or three. So we take the pair and triplet sets of this relationship that have real outputs, the pair and triple sets of this relationship that have real outputs, the pairs and triple sets of this relationship that have real outputs. And then we have our list of possible plural partial sets of this balanced dynamic. And guess what? Every constant in nature is attached to one of those. Every constant in nature. That's a fast step. We went from our simplest possible universe, being the hyperbolic figure eight not internally and externally expressed inverted as the n hypersphere of maximal volume, which has this whole hyperbolic construction. Some magic scale within that construction has the most symmetry. Okay, and that construction has these 5 exact boundaries. We have numbers, we have hyperbolic equations that'll allow you to get the accuracy you want, so they're infinitely defined, right? That's a big step up from the 5 digits we had, and we're taking them seriously. But when we do, when we guess that that hyperbolic division really is what's making that action, then we can look further into the pattern for a pattern. We can look further into the constants for a pattern. There, that's what's brought us to looking at the constants here. Yeah, no, this is fantastic. Let's look at the pattern now.
It is fantastic. It means we can basically manipulate matter.
Yeah, that's the goal.
And really change it from one thing into another.
That's absolutely the goal. We have to understand what matter is, what all of its actual internal boundaries are, why it has the specific expressions that it has from those boundaries, right? It's kind of the same thing. All right, so let's zoom out just real quick again to look. Here's the poster we had back there, the updated version. There's been a couple changes, so those of you keeping up with this, there have been like maybe 5 or 6 changes. I'll put the new one again with this video. All right, there's 8 rows in the way we've arranged this. There's a total of 288 constants. We left up on the board over here, 288 in the top left corner. And it breaks down in several ways. And 3 of the ways happen to be by products of 8, 18, and 32. The one that I'm showing in the poster right now is, of course, the first one, so 8 by 36. Okay, it would be very wonderful if a viewer watching this would be playing around with this construction and find the symmetry way to rearrange the same equations into an 18 by 16 grouping. I hope that makes sense. 18 rows, 18 columns, 16 equations in each column. Okay, or 32 by 9, or you can 9 by 32. It doesn't matter which way, right? So that would be really interesting. I'm going to be trying also. We have a lot of projects on our plate. Let's focus on why. First of all, the pattern here is overwhelmingly obvious that there is a pattern. You may have never heard of the Leibniz gate constant, but remember how I told you every constant in nature is attached to exactly one of the partial sets of our decomposition structure, either the pairs or the triplets. This is one of the pairs, J1 minus J2. This is a column of them. And this gives us an expression of a constant of nature. The left-hand side is a measured constant of nature. And we found this arrangement in our hyperbolic decomposition structure matches to it. And I hope you're seeing a pattern happening here. The only thing that's changing is the mass of the triton, the mass of the deuteron, the mass of the helion, the mass of the tau, the mass of the mu, right? Mass of the neutron minus proton, and so on. There's a lot of symmetry happening here, and they're all telling us a constructive arrangement that's expressing itself with these masses, with the whole gambit of masses. Do you understand the importance here? We're talking about a simple geometric arrangement in which it's stepwise going through all of the masses. that offers a level of understanding as to what the masses are, way beyond what you may have been looking for. Right? All right, well, I want to start off here. This is a beautiful column, but let's go all the way to the left column, the one that's of thetas, je theta. Let's say you have no familiarity with any of the constants in nature yet. You may have heard of the speed of light or heard of the gravitational constant, but maybe that's it, okay? Or it's a long time ago and you've just forgotten everything about it. All you need to know at this point is that left of the equals is the symbol we're using to represent a constant of nature, okay? It might look kind of complex, but that's for historical reasons. In some cases, I made them simpler to try to make them simpler. Eventually, we're going to make them all simple just to match the logic in the naming scheme, right? But they have a lot of historical importance right now, and we're trying to stay with that as much as we can, unless there's a real simple, obvious simplification to do. All right, so here's a constant of nature that happens to be achieved. This is what this prescription is telling us. When you put together these boundaries exactly this way, multiply it by pi, and then multiply it by this right-hand side of our factorization equation. Zeta of 2, I think we mentioned this like maybe a while ago, and je theta squared. This is our angle to get to our je r, or 3, or je 3, or je 4. Right? Okay, so in terms of je theta squared, in terms of revolutions in our hyperbolic decomposition, this geometric action, a square root of something countering the square of something, and that something happens to be zeta of 2, a two-dimensional zeta divide, interestingly, okay? And under this specific arrangement of the Planck boundaries and the Planck, or the mass of the electron. So the Planck length squared, the Planck mass, the Planck time, and the mass of the electron. And the mass of the electron, we'll get to hopefully on this same video, is also defined in terms of these Planck constructions. So everything ultimately comes down to just the Plancks. Okay? All right, there's another constant that's just 2 times it. Okay, cool, same construction. But here we go down the list, and now we notice another one that has the same exact setup with 1/2 instead of a 2 pi, and 1/2. Now, these are not exactly the same. These are not exactly the same because the plus changed. We have a proton instead of an electron, right? But sometimes you will see expressions that are exactly the same. This. There's a constant of nature that shares the same symbol as the reduced Planck's constant, or the Planck's constant, okay? Same symbol, but it's got the electron volt and the second, the unit second in its construction. Okay? This is, I mean, if you haven't seen before that the units themselves are buried in the constants, they are the conversation, really. The units and constants are the same conversation. Here's maybe your first beautiful clue. We'll be running into more. Here's another one. All right. Keep going down. A lot in common, a lot in common. Wait, was there one here? Is that copy? Not yet. This one. What's the difference between this constant of nature and this one? Sure, the name is different, but don't look at the left-hand side of the equal side. What's the difference on the right-hand side?
They're the same.
They're the same. That's weird. Well, why do we list both of them? Is that a typo? No, this is a different dimensional expression. This is a big mind-blowing moment. Wait a second. In the constants of nature, there are multiple constants with the same strings of digits, but the dimension that it's expressing in is different? Yeah. 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 Wait, what does that mean? That means that there are literal relationships between dimensions that are exactly the same relationship. There's some geometric story going on. Okay, beautiful.
Sounds like an interface, by the way.
Uh-huh.
Right?
Yeah. Keep going down. Notice the electron volt starts playing a very serious role. And then what happened?
Oh, which is zeta of 3.
Zeta of 3 instead of zeta of 2. Well, that was pretty. That was kind of pretty. I mean, how many of these have we got? Let's a little more. There. Now I can barely fit them all in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 of them with the zeta 2, then 2 of them with zeta 3s. Interesting. That's a chunk of the constants of nature that all have some symmetry in common. You probably see in the symmetry. I hope so. It's really beautiful, right? It makes you want to learn more about the zeta function. It makes you want to get more familiar with this hyperbolic decomposition structure. Right now we're only looking at the column of theta, so the rotation story here. But you can see that there's definitely a pattern happening, and then that pattern slightly changed in an interesting way. This is Apries constant, if you've heard of that, zeta of 3. Here, we got I got a space here because the pattern certainly switches, right? Now it's not zeta of 2 or 3, square root of that. Now we got E, which is what? Euler's number, to the negative Euler-Mascheroni constant, divided by 6. Do you remember what this constant is?
No.
No? It's the one, how much detail should I go? If we're taking the graph of y equals 1 over x, okay, it looks like, let's say this is 1, 2, 3, 4, 1, 2. Okay, it goes to 1 and 1, and well, it's better than that, something like that. It gets closer and closer and closer and closer to the origin, and as you go left of 1, it gets closer and closer to the x-axis. All right, now let's cut it off at 1. We're going to look there, and now I'm going to draw zoomed in a little bit. No, I don't need to zoom in. There's a lot of fun relationships we can talk about building here, like the 1 square relationship with E. Have we talked about that before? No? If you wanted to go, well, there's a 1 square right here, meaning there's an area of 1 square, right? 1 area. Now, if you want to go under the graph, and you have to stay under the graph and you fill in paint until you have the same amount of area, but now you can't go above that line. How far do you have to go to the right?
It would be a little further.
Yeah, it would have to be past 2, right? But it turns out it goes all the way to E. You'd have to go to E. And now if you want to do it again, you'd have to go to E squared, and then E cubed, and E fourth. So if you're tiling in 1 square areas, now you're counting in powers of E. That's interesting. There's a square 1 relationship built into E. Right there. Beautiful. There's lots of relationships, but look at this one. If you were to now say, all right, we have this smooth tiling. I do need to blow it up. It'd be easier to see.
But I can kind of see it gets stretched further as you go along.
Yeah. So imagine instead that we quantized it instead of smoothly did it and said there's a step there. We start here and say a block. Let's make a staircase, 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 staircase. Do that the whole way. Okay. And then you want to add up. Well, if you add up the area under all of this and add up the area under all of this, the staircase will have more area, right? If you take the difference between the areas, you get the Euler-Mascheroni constant. Think of this, what this is implying. If you smoothly connect the hyperbolic logarithm, the graph of y equals 1 over x, if you smoothly connect it, you get a certain area. If you quantize it, you get a different area. The difference between quantized hyperbolic and smooth hyperbolic is that. Okay? Now,
I don't know why that's significant yet, but okay.
Oh, it's significant because, well, think in calculus. The method in calculus, the big genius insight in calculus is that if you don't know how to do something, like take the area underneath this curve, just don't know how to do it, then you can invent a whole new way of looking at it. Like, let's pretend we stripe the whole thing up until all stripes, right? Just get the idea. They can be thick stripes at first, and we're going to approximate the thing we want. And then we can find a way to let a computer do that thing, but do many times and really skinny stripes, and then we can approximate it really well and get an answer, right? We can invent a method for getting there. That method relies on the notion of cutting things up, quantizing it, right? Here, there's a built-in relationship somehow, a relationship of calculus too, not just chemistry, but relationship of calculus written in a quantized versus smooth relationship built into this structure. And it becomes a very valuable constant in math.
Because now it's no longer approximated, right? We can actually calculate it exactly.
No. There are, well, that's a really fun thing to bring up. There are numbers we can calculate exactly, numbers we can write down, we can talk about coherently, precisely, and we call these rational numbers. Makes some sense there, right? We have rational numbers, we include fractions, but the fractions can be anything on the top and anything on the bottom, but they're going to be whole numbers. And they can be giant, so you can do lots of things with these rational numbers. One important thing you can do with them is define them. You can write them down. I don't have to take more than the whole board even. I just write them down and you know what's being meant. In fact, there's no confusion if you take that information and give it to someone else. It doesn't get changed and lost because in the error of what was said. It's a clear idea. If you want to write down E, we have become familiar with this number, and so we commonly write it, or pi, or the square root of 2. An irrational number is a different class of numbers. It's a different character that doesn't have the same coherency and properties that of other numbers like 1/4 or 3/7. It's a completely different thing because it can't actually be written down. If you want to give me the idea of what the square root of 2 actually is by giving me the number, and then going on forever and ever and ever and ever, and you're still not done, you've never ever given me the number. You can't give it to me. You can't give me all the information. Writing down the symbol in this case requires you, as the observer, to remember, oh, we're talking now about an irrational number, and this is a thing we can approximate. It's not a thing we can talk about exactly. Really cool. It's good to keep these things separate, right? These are in the category of things we can't talk about exactly. The things we're really interested in, they're geometric, right? In fact, you can talk about square root of 2 exactly in 2 dimensions. In 1 dimensions, the idea that there is a one-dimensional number whose square is 2 is wrong. There isn't. There isn't a one-dimensional number whose square is 2, right? It would, yeah. There's a real good approximations you can always go, but there isn't an actual number, a thing that can be written down that can then be squared and turned into 2. It doesn't exist, interestingly. All right. So that was from your question about numbers. What did you ask exactly? I think I lost track.
Well, actually, you answered the question because I wanted to know. I thought that we would be able to get an exact area of that curvature. We can't get an exact.
We have many, in fact, many of them written on the board there, and the poster we had it before, relations related to the primes and a lot of other geometric relations that give us exact prescriptions, so closed forms for getting this number, or 2 times this number, or e to this number, things like that, right? Many of those. So it's well known, it's got a lot of connections and relationships, the foundational relationships in geometric algebra. So it's a very important number, very important. And here it shows up in, what's this? That's the electron volt. Let's see, let's go here, electron volt. We're going to NIST, if you haven't been there. CODATA, NIST. Okay, here's all the ones that are related to electron volt. This is the one I meant right there. This gives us a number, right? 1.602.176.634. It doesn't say ... It doesn't give you parentheses with the error bars, and then says times 10 to the negative 19 joules. So how do we read this? It's a number in the dimensions of joules. That's what the J stands for. Okay, this 10 to the negative 19 is the scaling in joules of this number. Okay, but what it means to just stop for here means that we're using this constant, because look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits. It's a good one. We're using this constant as the definitions for the coherent bases. If it doesn't have a measure for error, then it means we've defined this one as that. because that was the closest to our actual measurement, and we're actually using this one for the definition of the bases. Interesting. Cool. That's what exact means. That's what exact means. Okay. Now don't get confused. It doesn't mean that it is the right number exactly. It means we're using it right now in our best story for defining the coherent base. We've updated these many times and changed that exact number, is why I'm saying. So just be aware. It doesn't mean exact that way. It means we've defined it as exact. Okay, beautiful. So let's go back. All right, so this Euler-Mascheroni constant shows up in the electron volt. This construction, notice, is almost exactly the same as we go down here. But what changes, so this is just the electron volt, okay, which involved J1 and a Planck charge boundary, which, by the way, these two multiplied together is the electric charge. It's just E, the electric charge, okay? So here's the electric charge, 1 over the electric charge, related to this sort of construction, related to the quantizing and smooth interactions of hyperbolic space, of a hyperbolic relation. Okay, some relation there, and there's 1, 2, 3, 4, 5, 6. Oh, and then this one changed. Interesting that there were 6 of them. They're all being divided by 6. And these are like hyperbolic splits, you might think. 6 splitting hyperbolic splits actions. What else do I want to say? Oh, this constant. This is the electron's charge divided by the mass of the proton. Wait a second. Why is it the same thing as an electron volt? Why has it got the same exact structure? Look at this. These are all similar, right? This is a completely different thing. The electron's charge divided by the mass of the proton also has this same geometric thing that makes it. Wow. The constants of nature literally only are the relationships between the bases, the dimensions. Bases are dimensions. These are the relationships maintained between the dimensions. Remember, this symbol here is our inversion boundary in our hyperbolic space. The actual scale in our hyperbolic space where we have the most symmetries, that's where we're inverting. So here, these constants are expressions of that inversion that all do a similar thing. Beautiful. Okay, this is the megahertz. This is a derived constant. Okay, so like I think you're building with a building block, and then you get to a certain point where now all those building blocks came together to make a bigger building block, and now you can use that building block, but only to build with it. If you want things smaller than that building block, like the first ones did, you have to still stick with the smaller ones. But if you want to build something really big like a mountain, you can start building with that big one now, right? Yeah, this is to think of. The megahertz is a derived unit related to the second. The second is the base unit. But there's a derived unit, there's a conglomeration scale in which the action of seconds, the action of time, literally become a new unit that you can choose to use as action. A natural built-in partition unit, right? Because the Lego blocks, they have to be fitting in, so there's lots of places that they actually have intersections.
Well, that's also kind of mind-blowing, because time is one of the boundaries in there.
Yeah.
So we're deriving a unit of frequency.
Yeah. Okay. Here's the atomic unit of force. That sounds really cool. And it's got a bunch more boundaries than the ones in here. It's got J1 to the 6, but on the right-hand side, it's the same J theta squared, but now it's got the 6 on top and Fibonacci factorial constant squared on bottom. Fibonacci factorial? Wait, what is Fibonacci again? What is Fibonacci factorial? What would that mean? Fibonacci is the simple sequence of decomposing something, the simplest ongoing sequence you can really prescribe, right? And here we're saying we're squarely Fibonacci factorialing. We're breaking up like Fibonacci under a square balance. Interesting. All these were squared. Okay, and then there's a break. Now, what's the difference? We're now in expressions of 3 of these rotations. So we're collecting 3 rotations at once, and look at this. Now, instead of e to the negative Euler-Mascheroni on top, we have the Giesking constant divided by 6. And down here. Oh, and down here it's divided by 8. Really, really beautiful set. Let's go a little bit faster through them now. This is the domino tiling constant, now divided by 6. Power of 4 this time. Really beautiful. We got power of 5 now, and there's 4 expressions. This is the rabbit constant to the 5. Okay, this is the goat constant. What is the goat constant?
It's the tether length at which you would have for a goat for it to graze exactly half a circular field.
Exactly. And then we have, notice the 18, we have 32s. This is the golden ratio. A lot of interesting symmetry happening here. Look into the structure and notice no matter where we go in the pattern here, everything is being made up of just the same exact type of arrangement. We have some sort of geometric expression, partition action like J1. We have boundaries that are the Planck boundaries, or we can use other mass ones that are built from the Planck boundaries elsewhere. And then we have the right-hand side, which tells you how we're inverting in our hyperbolic space. What does this one mean, by the way?
That's limit escape function, right? It's
Yep.
full argument of it.
Yeah, that's S is, here's 1 and here's -1. S is the unitary lemniscate, the one that goes to 1 and -1, crosses through the center, the lemniscate of Bernoulli. S is the actual length of its arc, the whole length. So start at one point and go all the way around until you come back to that point. That length is a distance that gets a number, okay? And that number is S. Arc length of lemniscate. Cool. In fact, a lot of our other geometric constants are quite related to this one. There's other lemniscate constants, right? There's S, there's L, which is the length of one petal. There's L1, which is the length of 1/4 of the whole thing, or 1/2 of one petal. And then there's L2, which is pi over S, which relates pi directly to all of these. Okay? These are all hyperbolic constants, but if it's the first time you've seen S, this is the most beautiful place to first see. What's being suggested here is that the constants of nature, these two specifically, are being balanced under a lemniscate balance. What's interesting about a lemniscate balance? It's the inversion of a hyperboloid, right? The inside balance, that the outside would be a hyperboloid. Okay? Then we get the magnetic constant. This is a central one in the story of making sense what's going on. Okay? Why? Because our story is that we're decoding the Planck boundaries under the hyperbolic Mobius construction, right? Whose scale parameter is the Planck mass boundary, and whose roots are J1, J2, J3, and J4, and whose partial expressions of those roots show up here. Jr, by the way, or Jr squared, is equal to J3 times J4. So right here, these two together, our 2 set right there, is equal to Jr squared. There's lots of other relations, but the one I want to focus on right now is that this constant is super central because out of all the construction, out of all the constants in nature, you notice we got boundaries, 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 boundaries. Look at all these boundaries that are made out of the Planck constants. This is made out of the atomic mass constant, but all these different kinds of boundaries. We go back up to that one right here. Its boundaries are the inversion boundaries out and in. It's the only one. It's the only one that has that. Making it special in a couple ways, but constructively special because our construction always has this story to it. 1 plus some action times by this inversion boundary. It's the one special boundary in the geometry. This is a really important constant. It's the only one whose external boundaries are the same as the internal ones, making it unique and important and central to the story. But also, as you've probably noticed, its primary action and its terminal action are also only made out of the j's. So this one's very central. It's got this central description for the boundary arrangement. The external projection of this boundary is the quadrants, right? It's -4 pi if you put all those together. So that one's negative of it, so this is equal to 4 pi. All right, so the quadrants and not the product, but instead half the two-dimensional product divided by the one-dimensional product, and then take the square root. We're taking the squares of all of them. We're taking the square roots of all of them. In one case, we're adding the squares together. In the other case, we're dividing the square roots. Two interesting operations being balanced against each other from the same hyperbolic roots. Okay, that's a really beautiful constant to kind of start investigating this symmetry pattern we're making sense of. But remember, the goal here is to then get insight to what's going on. Get insight to how we can manipulate the actual intersecting boundaries, the Planck construction inside of the actions of quantum mechanics, right? So this one's really informative for that story because we need to map exactly the exchange there, right? This is the constant, the magnetic constant on which that symmetry is most present, suggesting that our actual manipulation technique will be magnetic.
Magnets. That would even work.
Yeah, magnets are a great introduction to the mystery actually in the world because it's difficult to dismiss. It got Einstein when he was a little kid, I think 8, right? His father showed him. And from then on, he knew there was a hidden mystery to be uncovered. You couldn't convince him otherwise. That, and then he started thinking about light. There was mysteries there. Like, what would light look like if you sped up to the same speed? How do I visualize that? You know, these things he wrapped his mind around for a long time. And those are really fun things to wrap your mind around because under the process of doing that, whether you achieve your goal or not, the attempt is literally your consciousness reaching for a comprehensive understanding of something that surpasses where you're currently at. That's what the whole process is. So even if you fail, your brain has been trying to reorganize things in a way that's more coherent. And that's a fun and important practice to keep your brain, going. All right, well, here we go. We can go through many more of the pattern, and you can see from a distance, even without knowing what these constants are. They're all defined in the legend, by the way. Hyperbolic figure 8 naught divided by 18, r cubed, twice. And then now it's half of that, just the Giesking constant. Times this by 2, it becomes that. But that's what changed here. And we also went to the fourth. Interesting. Okay, our 1832 constructions are really central. We know what those mean even. That's very helpful. But here, this is a descriptor who's taking our whole hyperbolic figure 8 naught and dividing it by the 18 charge boundaries. Okay, in some volumetric way, r cubed. Interesting. There's a lot to see here. Now let's try to be extra clear. Our goal that's carried us to here so far is to take the whole set of constants and to try to end up with the most coherent geometric algebraic representation of them and the smallest symmetry set we can find. Yeah, that's a built-in goal. We're trying to make a set that's impressive, not every parameter requires another something in the legend. So you want the whole set of constants in nature to be composed from the minimal set of things. And right now we have it being composed from 5 Planck constants. N is equal to 5, or red N, and blue B is equal to 7, our break and scale symmetry. It's important to us, so we're coloring it and labeling it special. 5 is right there at the base, in the sense that there's 5 actual dimensions. There's 5 bases, right? Seconds, meters, coulomb, kilograms, and Kelvin. There's 5 of them, so we have 5 bases. That's the first important thing. The second thing is that as we scale out using the smallest possible base in that balance, then the easiest or simplest way you could possibly scale out has a break of scale symmetry of 7. So if you're making some closed loop, let's call it a circle, that's the simplest one, right? To build more coherent closed loops, or to find a closed loop of bigger scale, you have to build from the same size at first. So one circle surrounded by 6 more circles gives you your second scale, a total of 7. So our break and scale symmetry of 7 built in, meaning we're having a basic structure whose internal parts are as simple as possible. Now, we also have our hyperbolic relationship that partitions all of these things, right? So our j's, j1, 2, 3, and 4, and jr, and j theta. I've colored green the digits that extend what's currently known, okay? That we know this Planck time, 5.3912, from many routes in the constants of nature. We don't know those. That's coming from the equation we're assuming is leading to them, right? So all of these j's are new, because they're coming just from this equation, and that's entirely new. So that's why those are all green digits. The Giesecke constant, all well-known, hyperbolic figure 8 knot. Catalan's constant, directly related, of course, to those. It's just at a different angle. And the domino tiling constant. Okay, all of these constants, the power tower of I, or just I, pi, pup, the universal parabolic constant, then all of our lemniscate constants, and alpha and delta phi gamma constant. Then we got the QRS and the associated QRS constant for bifurcations, right, related to these two, and some more hyperbolic constants. These are all well-known central geometric parameters that we're composing our entire map from. I'm sure you've heard of some, Laplace limit maybe, the Ramanujan's first continued fraction constant, or just the regular continued fraction constant, or the golden ratio, everyone's heard of. Right? Paris constant is the rate at which the golden ratio is approached in the continued fraction form, which is interesting. The continued fraction shows up in several ways here. So it's playing an operative role that can bring us some comprehension. So telling that story is going to be very, very important. We're approaching it, we're trying to figure it out. But if anybody wants to help us figure out that story, we have several clues now that suggest it is part of the central story, right? This right in the gamma function itself. All right, these are all Fibonacci related things, right? This reciprocal Fibonacci constant, or the Fibonacci factorial constant. The rabbit constant is Fibonacci related, right? And we end here. That's where we're at so far. This also gives us 5 bases, 5 derived bases or units. And here's just definitions of our functions that are on the screen. Here's our functional structure. Just this one equation tells us our whole form, and our partial form tells us these. I think that's really, really fantastic. Let's just assume that there's some of them that are still wrong. So we're going to keep trying to polish and make it even better and better as we can. But as we do, it forces us to keep looking into it. And the goal isn't just to have found a pattern in the constants of nature. The goal is to then get to tell the story for why, right? We have a story developing now, the story of the hyperbolic figure 8 knot and the n hypersphere on the outside. And we have physical 4 different boundaries maintaining that balance on the outside. We have the exchanges being maintained these ways. Now, what needs to be understood is how do we use this prescription to then build a machine and modify by these exact values, to use these exchanges on purpose, right? That's really going to be the goal. So, all right, I want to jump now. Where is it going to be? This one. I'll show one we have a symmetric gamma function before I get to the Planck constants, which are the foundation of all of our structure. Beautiful to see. First, I want to show you the what's called the symmetric gamma function. And this is a combination of 3 things. I think it's pi to the negative z over 2 times gamma of z over 2 times zeta of z, where z is my complex number x plus I, y. Okay, so it's 3 things put together. And you know, before we looked at the gamma function with the phase plot, and it certainly wasn't symmetric. This one's known as the symmetric gamma function when you combine all 3 of them, and it took a long time to make it because anything with the zeta function is kind of slow. But here we go. Okay, all right, something's interesting happened there. Interesting. We're zooming in. Oh, wait a second. It is starting to look symmetric.
Oh.
Interesting it wasn't symmetric at all scales, but now it's quite symmetric. Not perfectly if you look close enough. Do you see the anti-symmetry anywhere?
Mm-hmm. They're
Where?
a little off-shifted.
Yeah, the colors are a little bit off-shifted, but the shape is quite anti-symmetric in 2 ways, this way and this way, right?
Yeah.
That's interesting. That's beautiful. That might be a clue that helps visually parse what the gamma function and zeta function are doing together. And if you find a combination that becomes more symmetric, it might be easier to tell the story. Yeah, anyway, I think that's an interesting clue, because ultimately what our hyperbolic story is a story of how you quantize and smoothly connect. That's what we're really looking for. There's 2 extremes in the story. Things are being quantized up. The charge boundary being 18 ways, the mass boundary in 8 ways, and so on, right? There's a fixed whole number of pieces of different types of things that are all smoothly connected. So there's a smooth story and a quantized story, and hyperbolic stuff already connects smooth and quantized, which is very interesting. So let's move to viewing again. Planck time of x plus iy in that space. Okay. What's going on? How is this related at all to the Planck time? This is the complex phase plots of the Planck time boundary, the hyperbolic boundary that's defining the Planck time. And its argument is just x plus iy. What are you seeing?
A couple ticker tapes or something.
Okay.
Some receipts and stuff.
It's almost like one-dimensional until we've zoomed in enough, first of all, right? It's like a big line, but that line's made up of a whole bunch of line segments going the other way.
It's like code running. Oh.
Yeah, and there's a whole bunch of like rainbow connections that phase through it. I want you to pay attention to the branch cuts. Some of them are lit white, and some of them are dark. Okay, this one's dark, this one's white, and watch them move.
Oh.
You see that?
Awesome.
I'm going to do it again for you to see, but then watch how fast they move based on how far away they are from the center. It changes. Interesting.
And that looks mirrored also.
Interesting. Watch the branch cuts dance. At top, they're doing really fast, and down here, they're much slower. Towards the center, they're slow. Towards the outside, they're really going like crazy. Right? It's faster the further you go out. No matter how much you scale in, that stays true. Interesting. This is kind of a new thing, a new way to look into this, right? First of all, it's to have a hyperbolic boundary matched to the Planck time to begin with is a new thing. So that's a fantastic thing. I'm going to look into all of them with an argument being the same, and then we'll look into all of them with the 1 over x plus iy as the argument. So this is now the Planck length. This guy.
That looks like, but no, it's blocky.
What?
You gave Space Invaders. Oh, now it's that's very interesting.
That's definitely different than the last one. But what does it mean? What's going on? Look at this branch cut here. It's not dancing at all, but those are. Huh. All right, let's go to the Planck charge. Hopefully, like me, you're at this point like, I have no idea what I'm seeing. This is just completely new. I have no idea what this is. That's okay. Just getting introduced to it is interesting. This is what pops out as the phase representation for the Planck charge boundary. First of all, notice this weird shape for its outer edge.
Kind of like the zeta thing.
Kind of like the symmetric gamma function.
Oh yeah.
Interesting. That's really cool. It just keeps. And then we have a bunch of little quantized dots in here. The column gets twisted or something, wrapped up. There we go. Beautiful, right? Intriguing. What's going on? On this scale, it's a lot easier to tell a story of what's going on, right? These are all phase representations, so you know you get a whole rotation if you go from red around the colors back to red. All right. But on the larger scale, what was going on with that structure and shape? What is that? All right, let's try the Planck mass. I'm doing this in this order on purpose because I find the inverse representation to be even more awesome. Saving the best for last. Uh-oh, immediately I'd say, except for being turned like this instead of like this one looks just like Planck time. It has all the major features I noticed in the Planck time, right? It's made up of stripes this way, it's long and skinny, but they're doing the rainbow thing. Wow, okay, that was good. Interesting. And at some point, we zoom in enough where you can actually see the individual branch cuts again, and we see them dancing around. Catch up. Yeah.
It's the same.
I hope.
Pretty much that's what we're talking about.
Yeah, I hope you're starting to see it almost like a balloon animals twisting. There's a twist happening here, another one happening there, or a roll around from here to there, right? Okay. There's some sort of geometry we're talking about here. There's interesting features you may have not ever come to without looking at that zoom, the way the things are dancing around. Okay, one more. Planck temperature. Interesting.
Oh, this is a much different brand.
Yeah. Whoa, it's gorgeous. Look at this structure. Wait, what is the shape?
Looks kind of like an octahedron. Or two tetrahedrons.
Two tetrahedrons. Really beautiful. Lots of cool things happening here in this structural balance. And this is all just zooming in. Okay, so there's a lot of phase interference. It depends on literally what scale you're on. Hyperbolic space is extremely scale sensitive in its construction, in its order parameters. But if you going over all the dozens and dozens of actual powers of orders, there's a range in between, like say 10 to the 10 and 10 to the negative 4. All of it's pretty flat there.
Yeah, it just stopped doing all that crazy computation.
Yeah.
It just became still. Huh.
Gorgeous, huh? Okay. There's a good start. Try to figure out what these things mean. Let's look at them completely the other way around. Let's go backwards. We're going to go Planck time. No, sorry, Planck temperature. And now it's the same exact equation, same exact function, but we've inverted the argument to 1 over x plus iy and plotted the phase and zoomed in. And now this is what we get. This is temperature looked at inside out. We can see the squares dancing if you look close here. Really sharply, it's awesome.
There's a whole bunch of knotted rings. Now, as we're going to be looping inside out, oh, there we go. Stuff's happening.
Wow. The shape of the hole on the inside gets built in an interesting way.
It looks kind of like two cardioids overlaid.
Planck temperature with inverse argument. This is its phase. Interesting. If it's just by itself, remember we're not plotting them together right now, we're plotting them individually to get some insight. The whole story together is the best insight, but we're starting piece by piece. This is the Planck mass with argument 1 over x plus iy.
It kind of looks a bit orthogonal to the other one. The other one was, I think, up, down. This is kind of...
Yeah, the branch cut here, the first one is a figure 8, right? But it's full circle figure 8. It's not a lemniscate. It's not the lemniscate of Bernoulli. It's one that's gone like more the lemniscate of Booth that filled the full circle touching full circle. And then a smaller one, but same 2 circles again, smaller, inside and inside and inside as branch cuts. But then the hole on the inside isn't 2 circles this way and this way, it's 2 circles that way. It's beautiful. Wow. Looks like a lot like a magnetic field, huh?
Mm-hmm.
The Planck mass boundary in phase. We can represent it via surface plot, of course, but this is the phase plot, and we can do it in high resolution. So I'm using that to try to look into it a lot more right now. Let's do the charge. Same thing, but now with the Planck charge boundary. Another beautiful display. Look, this bubble on the left doesn't have a boundary around it. Interesting. There's a whole sequence of them going off to the left or going in. And now the bump in the middle or the hole in the middle has like 3 bulges to it.
Mm-hmm.
It's almost like charge is a kind of imbalance.
Yeah, an asymmetric thing. Charge is extremely asymmetric. This side has those little bubbles coming out on the left. That side doesn't. This asymmetry here is quite obvious. Yeah, that's a good lesson to take away. Charge is an asymmetrically applied thing. Let's do length. Oh, that's a new shape for the branch cuts. Yeah, could be a little creature. Wow. There's a lot to try to absorb here, right? It's a new way of looking into things. But if you remember, the colors are literally defining their phase. They're telling you something about where they are going around in a circle, going around in a cycle. All right, and now the one I saved for last is the Planck time, which is absolutely gorgeous. Now, keep this framed appropriately. Remember, the insight that you could measure time came to, as far as we know, the first person that came to is Alexander, right? The insight that you could measure time. You put up a stick, it has a shadow from the sun, and as the sun moves, the shadow moves. And you can literally use the distance change in the shadow to measure that time. You can find a way to measure it now, right? Now, it's not that nobody could do that before, but nobody had thought of doing it. It didn't seem relevant. Why would you do that? But think of how important this is. Something that didn't seem relevant back then opened a window to the entire future of humanity. The whole enterprise of science was waiting for someone to first figure out that measuring mattered. That's an important statement, right? It's important to remember how important it is to measure things, because your brain's constantly projecting your vision, making up the world. And if you get confused enough to think that that's what the world really is, to be so confused to think that your brain is the one out of all the brains that have ever lived that somehow magically just got it right, right? You can get really confused and miss the goal of trying to discover. The first thing measured, the first birth, I would say, for science was when Alexander decided, I want to measure time and associate a number to that measurement so I can compare it directly to other measures of time that I make. And, by the way, he also invented measures of space, systematic measuring distance, and maps. He invented maps. So imagine living in a world without maps. I mean, conceptually, it's like almost a starting point in mathematics, right? You're mapping all the time in mathematics. An equation is a map. Everything can be thought of in terms of a map. He invented the idea of representing distances, proportions, and so on a piece of paper or on the sand, but systematically, not guessing, not just looking and saying, oh, it looks kind of like this. Right? He wanted to actually put points that could systematically represent real differences and make maps. That's a big step for humanity. And it's also the birthplace of science. The idea of what time is, the thing that we're measuring, became a center point of the investigation now, right? It's the thing that's real. You're measuring it, it's real. What is it? So the bases of measure are these 5. This is the whole story of science, has been accumulating process of people figuring out to think of measuring something about the world and finding out more about it than just assuming what they already thought they were seeing was right. Measuring can be more detailed. You know, I mean, everyone knows you can't just tell how far something is looking off and, okay, that mountain's exactly, you don't know exactly. You don't know exactly. Your senses and your abilities are not honed that way. Measuring it gives you a magical power to literally look into the world in a way that your senses can't do. So the base of measurements was the first person or time itself was the first thing being measured, giving birth to time, giving birth to science. And now we're going to be looking at what is the phase plot for the Planck time boundary, the limit of time in the constructive relationships built into atoms. Okay, I think it's absolutely exciting to see anything at all there, but this is gorgeous. What do you see?
Figure eight.
Yeah, branch cut goes from top to bottom first of all, straight through, and branch cut circles, just like the Planck mass boundary, but now the other direction. Interesting. Over and over, smaller and smaller circles in pairs that are the same size again, just like on the Planck mass boundary. Isn't it gorgeous?
I wonder if each of those are 1 unit of time.
These are all the different quantized aspects of it. Yeah, there's quantized features to see, and there's a total number of branch cuts in here, right? It's not going to go to infinity. And what do you find in the center?
Oh, that's orthogonal to the figure eight we were initially looking at.
Yeah, and 2 circles in the other direction. This is where we're at right now. I mean, this is a stage that's phenomenally exciting because we have visual access in a new way to what the balances of nature are actually doing. We've pulled them apart into individual ones now, and we looked at them inside out and outside in. But there we are. I think that's a good review. I think the exciting thing to keep in mind is when we achieve the goal, and we're phenomenally making progress here, right? We have 5 boundaries and 1 prescriptive rule for how they're partitioned and kept together, right? And that gives us all the coherent constants of nature, the coherent set of constants of nature. That's fantastic. We're using this not to assume we're right, but to then lens how to manipulate it in a new way, right? How to code a computer to use the actual constructive boundaries in mass already to do things and transform things. So this is the main goal. And when we get there, it'll be different to live in the world. I don't know how long it's going to exactly take to get to that point where everyone has their own universal replicator and it takes in nitrogen and spits out anything you've coded in it before, all of your favorite things that you need regular access to. It just makes them there out of nitrogen. It just needs a source of the boundaries, and everything with mass has the boundaries in it. So yeah, that's going to change the whole world. We're not going to organize in the same ways. We're not going to be preoccupied with the same things. We're going to have a lot more open up to us. You're going to have all day to learn as much as you can about whatever you think is the next thing you need to be learning to enhance the way you can engage with the world the most. So to improve how you actually can access the world. Maybe you want to fly and get your pilot's license. Maybe you want to learn how to mine and understand the gems in the world. There's all kinds of things you can do when it's not doing it for money, when it's not doing it for prestige, but instead doing it to enhance the character you possess, right? The reason you might read a book is to learn the idea in the book and now possess it proudly and excited because that idea allows you to see differently. Every time you see differently, it enhances and changes how you feel in the world, right? It changes what you have as limitations and restrictions, and that feels different. So this is going to entirely lift the restrictions we've built in our modern construction, our modern attempts to try to, have power and control over each other and, be in charge. It's going to change the game entirely to where that's not even worth paying attention to anymore. Now it's how much can we personally learn? How much can we personally access the world around us and do things with it? And I'm really excited about this. So anyway, there's lots to be done. There's a lot more progress to be made. But if more people are interested in investigating the pattern and perhaps suggesting improvements, if you got to the point where you're looking at what's going on and you see an improvement to be made, please suggest. That's what we're doing, so save us the time. Yeah, and we're also trying to understand the pattern we currently have. So we're not spending all of our time trying to change the pattern. We're also trying to take what we have seriously, especially the things that group up really well, and try to understand what they might mean. There's a lot of nuance in the structure until you have the whole visual picture. It's a lot of conversation to have, but we're also trying to build the visual picture. So anyway, it's exciting,
Cool.
and that's where we're at.
Very good. Yeah.